In this, our last lecture on optics, we will deal with basically material related to quantum optics. The first law that we will discuss is called the inverse square law, and it's fairly straightforward. Beyond that, we will go on to something you may know from middle school classes, basically the structure of the atom. We're not getting too deep into that, just whatever is important so that we understand how light works. It would be related to a topic you think is incredibly complicated, called quantum physics, but for our purposes it's not going to be that complicated at all. There is a subtopic of that quantum physics which is fairly shall we say mysterious, or was mysterious at first, and that's the issue of black body radiation. It has nothing to do with black holes whatsoever, and it's not even black. It's the opposite, it's shining. But we will explain that. Then we will go on to a short trip across the universe, talking about what comes from where and how we know that. Here is a quick reminder. We're learning all about these optics because when we're looking at the stars, as in the picture below, we can see a lot of details of these stars. We can see the brightness or the intensity coming from it, and we can see the color. So first let's look at the brightness. It would make a lot of sense that the brighter the stars, chances are they're closer to us. Ends up it's a combination. They may be closer to us, or they may be really brighter intrinsically. The inverse square law for light is also true for sound and for anything else that propagates in all directions. The intensity of that goes down like the distance square. Here is something else whose intensity goes down, is the inverse of the distance square. Gravity. You may recall that we introduced the law of gravity, and the further away you are, the weaker the force. And although we have 3 dimensions, actually it goes down like the inverse of the square. That's because everything is surrounded by a surface whose area is proportional to distance square. An actual area of a sphere is 4 times pi times the radius square. You may be familiar with the area of a circle. That's pi r square, right? You may remember that from high school, where you were told pi r square. Well, we usually eat pies that are round, but pi r square. Okay, that's a mnemonic to help you remember that pi r square law. Now think about a balloon. It's basically 2 circles, one on top of the other. So that's 2 pi r square. Then you puff air into it, therefore the air must be making the surface area of the balloon larger than 2 pi r square. Ends up that it's 4 pi r square. But between the 2 and the 4, that's a math that is beyond the level of our class. Now think about, for example, a light bulb, as in the picture below, and the light from the bulb shines through a sphere of pi r square area at a distance of 1. Then look what happens to the area of that sphere as you go to twice the distance. Obviously you can see that for every square there are 4 square when you go to twice the distance. Hence power diminishes as the distance square. This is a slide we had in previous lectures. In it, if you recall, we could put at the back of a telescope a device called a spectrograph, basically a prism, that takes light from a star and breaks it with the prism into a strip of lights, basically along a Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. But it's not continuous. There are actually lines across the spectrum. This was the reason that atomic physics or quantum physics emerged in the first place. 100 years of such spectroscopy yielded the ideas that led to quantum physics. More on that in the next few slides. This is a spectrum that you get from certain types of elements: molecular hydrogen, neon, lithium, iron, etc., including the sun, a light bulb, fluorescent light bulb. You may see that some of these have bright stripes on them, some of them have dark stripes on them. More on that in the next slide. Let's look at this slide. Basically the stripe, when I'm looking at it, not with the eye, but rather if we, for example, put it on an electronic device, we can see how many photons or how much light is in each and every color. And we can see that we have an intensity and then bites in that intensity. In the next slide we will separate the two and see what is that smooth curve and what are the bites due to. Even before we knew anything about atoms or about that mysterious something called black body radiation, Kirchhoff, or Kirchhoff as most Americans call it, figured out that we can separate that light into its components in the following way. There is something responsible for the smoothness. We call it the black body source. If we look at the light from that, we will get a continuum. If we put a cloud of cooler gas along the way, then we would get a spectrum with bites in it. And if we look at the cloud and hide the hot black body source, we will get an emission spectrum, which is just the actual colors that are completely uncontinuous. By the way he looked at that was looking at the sun during a solar eclipse. You could see that cloud of slightly cooler gas called the chromosphere of the sun, and that gave all those emission line spectra in the bottom right hand side. If you looked directly at the sun through a prism, you got that continuum and bites, and he figured out something called the black body on Earth that gave the continuous spectrum. Let us start with the emission spectrum. As you are probably well aware, an atom is a protons and neutrons in the nucleus, and then an electron orbiting it. But it could be that you have just one proton and one electron, as in the picture enclosed. This electron may be in certain orbits, and the interesting thing about quantum physics is that those orbits are quantized. The electron can be in the n equal 1, n equal 2, 3, etc. orbits, but not in between. That was a huge leap forward in our understanding of atoms that came around from spectroscopy. Now if you have that proton and electron orbiting it, and you jump from the electron, jumps from the second to the first energy level available to it, it gives off a certain color of light. Those jumps actually are visible. The jumps actually that are visible are not to the first energy level but to the second energy. From the third to the second energy level, 656 nanometer between wave crests give us red, 486 nanometers between the fourth energy level and second energy level give us a blue, 434 is more towards the violet, 410 is very violet. Those are actual visible lines. The jumps to the first energy level, the Lyman series is in the ultraviolet part of the spectrum, and the Pachken series is in the infrared. So we're getting that emission line spectrum that we've seen in the slide, 2 slides before this slide. That is the origin of that light. Notice that if we had a continuous spectrum that ran through some atoms, what it would do to them is it would make the electron jump to a higher level, to further away from the nucleus, therefore leaving bites in that spectrum. But what is that original continuum spectrum? What is that continuum spectrum that comes from the surface of the sun, or that we can see on Earth? In the 19th century, those scientists that looked at sources of light noticed that if you take the spectrum from a glowing hot kiln, and this could be done with a glowing iron, for example, or stainless steel in steel mills, you put that light through a prism and you get a continuum. No bites. This was actually completely unexpected. If light was a wave, this would have caused something completely unexpected called the UV catastrophe. There would be too much ultraviolet or too much violet, but they didn't see any of that. What they did see is a spectrum that peaked depending on how hot the kiln was. It peaked towards the violet when the kiln was extremely hot, a little less hot, and it peaked towards the red. The person that first explained that phenomenon is Max Planck. Planck is usually referred to as the father of quantum physics, together with Albert Einstein. If you look at the stripe below, it's continuous, and the graph next to it is continuous as well. However, that graph is not flat. It has a peak. That peak, as I pointed out, depends on the temperature of the kiln, so to speak. That kiln called the sun has its spectrum peak at around 6,000 degrees Celsius. The kiln called Sirius has the peak at about 10,000 degrees Celsius. So those kilns have their peak at different colors, that is, different wavelengths. Interestingly enough, if the wavelength is longer, that is redder, the peak implies the star is a little cooler, or the kiln is a little cooler. Think about it. Before we even know anything about the star, we know how hot it is. That's kind of cool. Pun intended. Looking again at the black body curve, this time around, notice that this is for the same area kiln or star, you notice that when the temperature increases and the peak shifts towards the blue or violet, the area under the curve becomes larger. Basically, the brightness of the whole thing grows quite dramatically. Ends up that you just double the temperature, and the brightness will go up 16 times. Triple, and it's basically 81 times, which means 16 is 2 to the power 4, 81 is 3 to the power 4. Therefore, hotter stars emit way more light, even if they were the same exact size. One last light-related effect is the Doppler effect. If a source of light is coming towards you, the waves of light are going to be kind of condensed together a little bit. Therefore, if to begin with you had green light and an object is moving towards you incredibly fast, the waves will be squeezed and you may actually see blue light with shorter wavelengths. If an object is moving away from you and it's green, basically you may see it as red. Here is a story that I heard. I don't know if it's true. A guy comes to a judge in a courthouse for traffic violation and says, "Sir, I thought that this was a green light rather than red light because I was driving towards it, and because I actually, what happens is that when red light moves towards you, or when you're moving towards a red light, the waves are squeezed, and what I thought was a red light was actually green light." The judge, who knew physics, says, "Fine. No fine whatsoever for driving through red. However, you're paying 1 penny for every mile per hour that you were over the speed limit." In order for you to actually see that shift from red to green, you need to be moving at about 1/4 the speed of light. This is an example of what happens when two stars revolve around each other. The strip should be in color, should be a Roy G. Biv again, but rather than having continuous color with one type of line, you have pairs of lines. That's because as a star is moving towards you, you have some lines shifting one way and some lines shifting the other way. From moving towards you, it shifts one way, moving away another way. This is a tiny part of the Roy G. Biv spectrum, hence that separation. Those stars are still not moving at a fraction of the speed of light. Here is another picture of the same exact example. As you can see, as B is moving away from you and A is moving towards you, you're gonna see one shifts towards the blue, one shifts towards the red. Let's start with our promised tour. This detector of light is called radio telescope antennas, the same as your satellite dish in the backyard. Only it sees further into the universe because it's bigger. In principle, you could modify your satellite dishes in the backyard to observe the part of that spectrum. That part is called the radio. That's what you are gonna observe with your radio antenna as well. Radio broadcast is nothing but light. The wavelength of that light is fairly long, of order of meters or a few feet. Or in case of your cell phone, for example, your cell phone detects radio waves that are basically less than an inch. The material that emits this is not atoms directly, but rather something like a large conductor. Here is a large conductor that emits those radio waves, for example. These two blobs are kind of far apart. That little tiny dot in the middle, that's a galaxy that's 100,000 light years across, which means the distance between the two sides in this image is 1,000,000 light years across. These are what's called lobes from an active galaxy, radio lobes from an active galaxy. In this picture you're seeing an image of the planet Jupiter. On the right hand side, this is Jupiter in the visible part of the spectrum. Just a regular picture combining the Roy G. Biv together. On the left hand side you're seeing an image with an infrared telescope. What you can notice, for example, is that the great red spot on the bottom is that little dark spot on the bottom left in the left picture. That's because in infrared that spot is a bit cooler and we can kind of see a heat map of Jupiter in this image. Therefore the great red spot, which in this picture is kind of yellowish orangish, is actually cooler than the rest of Jupiter. Again, kind of cool, pun intended. Here is a satellite that's observing the universe. This is called Chandra Observatory. The Chandra Observatory observes in the X-ray part of the spectrum. We cannot see X-rays through the atmosphere, and that's lucky for us. Otherwise we would have been bombarded by X-rays from the universe the whole day long. Our atmosphere protects us from ultraviolet, X-rays, and parts of the infrared spectrum. We can see radio through the atmosphere, and obviously we can see regular light, visible light through the atmosphere, or else we wouldn't see the sun. In this image, which is taken with an X-ray telescope, we see Sirius B. The star Sirius, which is the brightest star out during the winter usually, is the brightest star in the night sky except for planets. In this picture, it's the dimmer star of the two. That is because Sirius, which is a fairly hot star with 10,000 degrees surface, has a companion that has a surface temperature of hundreds of thousands of degrees. Therefore it shines with wavelengths that are even shorter than violet. Whereas Sirius is kind of bluish, Sirius B shines mostly in the X-ray. The last couple of pictures will demonstrate the idea of a black body radiation, only this one is coming from all over the place. This picture is taken in a microwave part of the background, basically with dishes that can observe the same exact frequency as your cell phone observes, or very close to it. That radiation of light, invisible light since the wavelength is so long, coming from all over the universe, is one of the strongest proofs for the existence of the Big Bang. Of course, more on that will come later in the class.